Hi everyone, welcome. This is our last live of the day. We're going to do some quick GCSE physics revision. So if you're up to doing some revision before we end tonight, welcome to all of you who are regulars and who are joining for the first time. I'm going to do a quick poll so you guys can vote on which one you want to start on. Fission versus fusion, or finally Newton's laws. Okay, so I've started a quick poll, which should come up on your screen. If it's not on your screen, if you go to the bottom of your screen and you tap interact, then you'll be able to click on the poll and vote for which one you want to do today. So we're going to do a very quick physics revision session for all of you guys, and we're going to do one of these topics. And yeah, it will be a very nice quick revision session before we go to sleep. So, if you are joining for the first time, welcome. Make sure you give me a follow. Hi, ARU again. Hi, Kyla. If you are joining for the first time, make sure you give me a follow so you don't miss out on these lives. If you are a regular, welcome back. And please do like the live so that other people can join quickly and we can get started ASAP. Welcome, everyone. Welcome. Nice to see you guys. Yeah, we're going to do some physics. We did some bio and chem earlier today. Like I told you guys, I will be posting these on my YouTube account, again, so you guys will be able to watch over these later too. Welcome everyone. Welcome. If you tap on interact at the bottom of your screen, you'll be able to find the poll and you'll be able to vote on there so I can see all of your votes. Currently, we've got Newton's laws winning. But it is quite close. So do vote for which one you want to start on. And we're going to start very quickly so we can do a quick revision session. So choose whichever one you guys want. If you are just waiting there, make sure you tap the screen and like so that other people can join us. And if you're not already following, why the hell not? Make sure you're following so that you know when we're doing these lives. And so you can watch my revision videos, my quiz videos, and you can test your active recall and see how well you're doing. Thanks for the follows. Thanks for the likes, guys. I appreciate it. Make sure you're voting for what you want to start on. We're going to start the revision very soon now. Let's see what's winning. We have Newton's law still winning. It looks like it's going to be the majority winner. So we might not wait till that quiz is over or that poll is over. We might just get started. Welcome to everyone that's here. Welcome if you're new. Welcome if you're a regular. I can see quite a few regulars here. Thanks for the follows. Thanks for the likes. I appreciate your guys' support. Make sure you vote for what you want to do. And in the meantime, make sure you're tapping the screen to like so that other people can join and revise with us before we go to sleep. And for the people who are here for the very first time, firstly, welcome. Make sure you check out my channel. And secondly, if you haven't already, make sure you check out my revision papers on my website. I say revision papers, they're predicted papers for this year's GCSE exams. If you check my website out, christuition.myshopify.com, the website link is in my bio and on my Instagram bio as well. I've got predicted papers which I've spent so many hours making for you guys. I can't emphasize how long I spent on them, but you regulars know I always go on about how long it took me to make these papers. These papers are on my website. They're the predicted papers for maths. The maths ones are for AQA, OCR, and EdXL. And the science papers are AQA only, combined and triple science. Make sure you choose the right one, okay? Some people buying the combined one by accident and then asking me for the triple one. So make sure you choose the right one to avoid any mistakes. But really good opportunity for you guys to get the closest thing you're going to get to the real exams. Okay, the closest thing you're going to get to the real thing. Really good revision. I've made these papers of knowledge of what I know is going to come up this year because it needs to come up. And also patterns of what comes up year in and year out. So really, this is going to be the best thing you guys are going to get to revise from. So make sure you check those out. And don't forget, on my website, if you type in the discount code LIVE30, no space, all capital letters, you get an extra 30% off for coming from my live. And everything's already heavily discounted. So it becomes, I think each paper comes down to like 60, 70p per paper. And yeah, like I said, it's the best thing you can get to the real thing. So yeah, be patient, boys, says Sophie to somebody. Yeah, 25 seconds left. Oh, it's actually really, really close. Fission and fusion and Newton's laws, there's 2% between them, less than 2% between them. So I'm going to wait the last 15 seconds, see if anything changes. Is fission and fusion going to overtake Newton's law in the last 10 seconds? This is the closest one we've had before. Oh, no, Newton's laws has taken the lead significantly. So we're going to do, I know, it's very exciting. So yeah, Newton's laws has won, guys. So we're going to look at Newton's laws, which is a nice topic actually to end the day on, I think, because it's a nice and quick one to go over, and we will be done with physics revision for the day as well. So let's look at Newton's laws. Then afterwards, if you guys stay, I'll let you guys know about fission and fusion as well. Okay. If you're not already following, make sure you are following and like the live so other people can join us. And let's go through Newton's laws. So Newton's first law. Hopefully you guys can see this. So the first law states that objects will remain at rest or move with constant velocity. I'll explain what these mean. Velocity, unless acted on by a resultant force. Okay, so what that means is that an object will remain stationary or remain still, like my laptop is currently remaining still, unless there's a resultant force on it, unless I push it, right? It's going to stay still unless I push it or unless I pull it, because that's a resultant force. At the same time, it says it could be stationary or it will move with constant velocity. So also if something's flying in space, for example, at a constant velocity, it's not going to slow down or speed up unless something actually acts on it to speed it up or slow it down. Okay, so it's different when it comes to doing things around Earth and on Earth, because we have an atmosphere, so there's air resistance, right? But in space, if something is moving at a constant velocity, it will continue moving at that constant velocity forever unless there is a resultant force acting upon it. And that's Newton's first law, okay? So remain stationary or carry on going at the same velocity unless there is something acting on it, okay? Super, super important. So that's Newton's first law, okay? Newton's second law, can anyone in the comments tell me what the equation is for Newton's second law? We should all know this one. Newton's second law. Yeah, well done, guys. F equals ma, okay? So if you're asked to define Newton's second law, you can write F equals ma, and you could say, along with that, let's write it in red over here, we'd say that the acceleration, let's spell it right, acceleration of an object is proportional to the resultant force acting on it, and it's inversely proportional to mass, so to the object's mass. Okay, so that's what that equation tells us. F equals ma tells us that the acceleration is proportional to the force, okay, but it's inversely proportional to the mass. All right, so we should be able to define this. The acceleration of an object is proportional to the resultant force acting on it, and it's inversely proportional to the mass. All right, so that's Newton's second law. Okay, are we happy with this one? Hopefully that's a yes. If you are here for the first time, make sure you guys are following so that you don't miss out on our lives. And do like the live if you haven't already, so that other people can also join and know that we're revising. Okay, so I'm going to get rid of this one now. Don't forget, this will be on my YouTube account, so you'll be able to watch over it again. And Newton's third law of motion states that essentially, you can remember with the rhyme, every action has an equal but opposite reaction, right? So every action has an equal but opposite reaction. Every action has an equal but opposite reaction, okay? And what that means is if there is a force acting on something, there will be an equivalent force acting backwards onto that something, okay? Equal in size in the opposite direction. A good example of that is thinking about like a box sitting on the ground, right? If I've got this box sitting on the ground, yes, there's a force acting downwards, and that's the weight, right? But there's also an opposite force acting upwards, and that's the reaction force, okay, which keeps this object stationary. Okay, if this wasn't true, if there wasn't an equal but opposite reaction, then the box, because of its weight, would continue traveling through the earth. It would dig through the ground and continue traveling through the earth, which is impossible, right? That's not happening. So there's an equal but opposite reaction keeping it still. Okay, are we happy with that? Goodbye, Sophie. Yeah, inertia, ARU. Inertia is when an object continues to travel at a constant velocity or when it's at rest. Okay? So, you know, with Newton's first law, when we said an object... no, where's me? Oh, sorry, Kyla. Goodbye, Kyla. So yeah, when we were talking about Newton's first law, we said that an object will continue moving at a constant velocity, or it will continue being stationary unless there's a external force acting on it. That would be inertia. So when it's, I think I'm confused. So Kyla's not going, Sophie's not going. I don't know who's going. I don't know who's coming or going. Yeah, that object has got inertia at that point because it's staying at a constant state. Okay. So very good question there. If an exam question does ask you, what does inertia mean? You would say it's when an object remains at a stationary, in a stationary state or at a constant velocity. Okay, so that's that. So we've just gone through Newton's first, second, and third law. So hopefully we understand what these laws are, and we can now state them and be able to apply them. It's really important that you're able to understand them and apply them if needed as well. So now the question is, should we end there, or should we talk a little bit about fission and fusion? Because that was the second highest topic. Shall we go through fission and fusion? Or no? It all depends on you guys. If you guys really want to go over it, we're saying yes. Yeah, seems like most people are saying yes. If it's a yes, then yeah, absolutely. Okay, yeah, we can have a go at it. That's fine. Absolutely. There is a required practical, by the way. Okay, there is a required practical. It's the one investigating the force on acceleration, so Newton's second law. Okay, where you have like a toy car, like a tape, and then you put weights on it and you see how quickly that car moves, and therefore you can calculate its acceleration. There's that one. But yeah, if you guys are sitting there idly if idly is even a word, I don't know. Do like the live whilst we set up to do some fission and fusion. I'll cover this topic very quickly for you guys as well. Fission versus fusion. For you guys that wanted to go over that. Fission and fusion. So make sure you like the live. If you are here for the first time, make sure you're following as well. Please follow so that you know when we're doing these lives. But they will be on my TikTok, on my YouTube account as well. So don't worry about it if you miss it too much. Okay. Yeah, you measure the distance. Okay, cool. So let's talk about fission and fusion. So they're both nuclear fission and nuclear fusion. They're both ways in which we can produce, or rather not produce, because we don't like to say produce energy in physics. We like to say generate energy, right? So they're both ways in which we can generate energy in physics. Now, fission is something which we currently can do very well. We do it very well. We do it in nuclear power stations. Fusion, on the other hand, we're not very good at doing that yet. Fusion is something which occurs on our sun 24/7, and which is why our sun is able to produce humongous amounts of energy constantly, and therefore heats the earth and so on, right? But we are currently not able to do fusion very well, although we're getting better at it, okay? In 2022, last year, we were able to do fusion in Oxford in the UK for about 4 seconds. Okay, so 4 seconds is actually a huge achievement to even be able to do fusion for that long, because the previous attempt was about 10 years before that, I think, and they managed to do it for about 1/4 of a second. So then 4 seconds is a huge improvement on 1/4 of a second, right? Whereas fission, like I said, is something we do all the time. We're going to talk about why it's so difficult to carry out fusion. Okay, and I can tell you guys a little bit about how theoretically we could do it as well. But let's talk about fission first. Okay, so nuclear fission. Nuclear fission involves taking a large nucleus. Okay, and with that large nucleus, so let's say I have a large nucleus of uranium. I think uranium's 235 if I remember correctly. So I've got uranium 235 here, okay? Now, at this uranium 235, I'm going to have a neutron being fired here, okay? So this is a neutron. And this neutron is fired at this uranium. This uranium nucleus will absorb this neutron. And when it absorbs this neutron, it's going to split up into 2 smaller nuclei. Okay, so this uranium will essentially break into 2 smaller nuclei. And as well as that, it will break down into 3 additional neutrons. Okay, so that is the premise of nuclear fission. Okay, this is the premise of nuclear fission. We've got a neutron fired at a uranium 235, large nucleus. This nucleus then splits into 2 smaller nuclei. So you've got 2 smaller nuclei and 2 or 3 neutrons. Okay, these 2 or 3 neutrons, okay, will then carry on breaking down these nuclei. So they'll then be fired at these nuclei, and then they'll break those down into 2 smaller nuclei, and this continues. And every time one of those breaks happen, where one larger nucleus is broken down into a smaller nucleus, there's a whole lot of energy which is released. That was supposed to be a lightning bolt. So yeah, you can see how terrible my drawings are. That's energy being released. Okay, so a large amount of energy is being released. And yes, this is a chain reaction. All right. Now, this energy can be harvested, for example, by heating up a water source. That water source will turn... Oh, we're lost. We're lost. Okay. Let's go back a second. Let's go back to this stage here. Okay. I've got a large nucleus. I've got a large nucleus here, uranium 235, right? I've got a neutron. a neutron is fired at my uranium-235, okay? When I fire this neutron at uranium-235, I form this uranium-235 will split, and it will split into two smaller nuclei, okay? And when that happens, yeah, this is for triple science students. If this happens, 3 neutrons are also released, and a whole lot of energy is also released, okay? And this energy can then be used to do things like heating up water, which then turns into steam and therefore turns a turbine and therefore generates energy, okay? That's why you don't know this, yeah. Don't worry, it's late. Don't worry, Sophie and Kyla. Even I don't know my name at this point. So yeah, fission is this, okay? And when this continues happening lots and lots of times, it's called an uncontrolled chain reaction, all right? And if you want to control this chain reaction, can anyone tell me what we would use to control this chain reaction? I'm expecting ARU to get this. What do we use to control a fission chain reaction? Dum, 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 dum. Does anyone know it? No? Control rods, nice one. And for a bonus mark, can anyone tell me what those control rods are made from? So control rods help to control the chain reaction. The way that they control this chain reaction is they absorb neutrons. Okay, control rods absorb neutrons. So that means that even though there might be 3 neutrons produced, it will absorb maybe 2 of them, and so only 1 will then get to react. Actually, no. Good guesses. Bethany with graphite, ARU with iron. Control rods are actually made from boron. Okay, from the element boron. And the reason why they're made from boron is because boron is a very good absorber of neutrons. Nice one, M. Yeah. Boron is correct. All right, so that's that. Now, fusion. Let's briefly talk about fusion as well. Okay, so fusion is kind of like the opposite of fission, right? With fusion, we have, instead of one larger nucleus breaking down into 2 smaller nuclei, we have 2 smaller nuclei coming together to make a larger nucleus. Okay, so we have a smaller nucleus and a smaller nucleus joining together to make a larger nucleus, right? And lots of energy. Okay, now remember, not the 5th of November, but remember that nuclei are positive. Okay, a nucleus is positive because it contains protons. Okay, and because it contains protons and because they are positive, trying to force 2 very positive nuclei together is very, very difficult because they're extremely repulsive. Okay, there is an electrostatic, and a very strong one at that, electrostatic, static force of repulsion. They repel each other like hell, okay? They do not want to combine together into this larger nucleus, okay? And that's what makes it so difficult. To overcome this electrostatic force of repulsion, you need an extremely high temperature and a lot of pressure, which is only achievable currently on the sun. So we need millions of degrees Celsius. That's fine. Kyla, A for effort. Yes, fission creates a smaller nucleus, Yusuf, yeah. So we need an extreme amount of temperature, so extremely high temperature and extremely high pressure. Now, we are currently actually able to almost completely recreate the temperatures that we need for fusion. So we're actually able to do that on Earth currently, which is amazing, right? But the problem with it is we don't have materials which are able to withstand that temperature, because we're talking literally about millions of degrees Celsius. So theoretically, the way that we could get fusion to occur is if we were able to have the reaction happen in space, like a levitating reaction. Okay, and the way the way we could do that is by using magnets. So by using really strong magnets and holding the whole reaction in kind of space in the air, we could carry out fusion, and therefore there'd be no materials involved because it would all be held in the air, right? But for that, we need really strong magnets, and magnets that can also withstand all that pressure that we're going to be applying. So it's actually really mind-blowing the way we're doing this. It's really epic. So they are currently doing that up in Oxford. If you look it up on the news, the Oxford fusion plant, they're doing it, and they're doing it really well. Like I said earlier, they're getting much better at it, right? Within a 10-year period, I know in 2022, they did it for about 4 seconds. They were able to successfully carry out fusion for about 4 seconds. And I think it was last done in 2012 where they did it for about 0.25 seconds. So if you think about it, that's a 16 times improvement, right? Correct maths? Yeah, correct maths. So if they do that again, another 16 times over in another 10 years, or maybe less, that's going to go for over a minute. Okay? So the way I'm saying it should be the reason why I'm saying it has to be in the air is because we don't have any materials on Earth which can withstand millions of degrees Celsius. Question, what is it used for? It's used to generate energy. Okay, if we were able to carry out fusion, we would be able to generate so much more energy than fission or any non-renewable resources, and therefore be able to power the whole country or the whole world very, very easily. And the best thing about nuclear fusion is that it's a clean energy. There is no harmful waste products. Whereas in fission, we should know that fission results in nuclear waste, nuclear radioactive waste. And this radioactive waste is really difficult to dispose of. Okay? And because it's so difficult to dispose of, it's not a great way of generating energy. It's actually really bad for the earth in the long run, and bad for the people who have to do it. Yeah. In fusion, mass is converted to energy. That's correct. So yeah, very good. We're going to start to finish up there. Like I said to you guys, this will be on my YouTube account as well. So I will post this there. You will be able to watch over it again. But well done. Well done to those who managed to stay and listen to all of this. And hopefully it's helped you remember something, even if it's one fact. I'm very glad I was able to help some more. So tomorrow I'm working. So tomorrow I won't be able to do a live because I'll be gone. I'll be at work since like 6:30 in the morning till about 7:30/8 in the evening. So I'll be home quite late. I don't think I'll be able to do it then. So Saturday morning will be the next one. Okay, I'll post the video tomorrow anyway. But yeah, can you do gamma, beta, alpha radiation? Because I don't get that. Yes, we can go through that. No, Saturday, Sunday in the morning and in the afternoon, I'll do a live for all of you guys. So I'll see you guys then. And biology, please. Cool. No problem. It's absolutely fine. So yeah, make sure you guys are following if you're not already. If you haven't already, check out my website and get to sleep. And have a good rest of your week, guys. Take care. You're welcome, guys. You're very welcome. Well done for all of you for joining and actually staying through it, even though you don't do triple science. Bye, guys. Take care. Good night. See you in a bit, ARU. Bye, Kyla.